Despite blooming research on quantum materials, many scientific questions are still open to this date. The magnetic neutron scattering probability is directly proportional to the magnetic scattering function S of Q and omega that assesses the macroscopic Hamiltonian encoding the fundamental magnetic interactions in a material. Novel multiplexing neutron instruments now allow a simultaneous probe of thousands of different points in four-dimensional Q and omega space. Thus, in a short time, a full picture of the magnetic excitation spectrum in a material can be measured. However, this tremendous improvement in the data collection generates new computational challenges. Current analysis strategies require experts to manually go through each dataset and mask out spurious background features as shown in this figure. Being a notoriously slow process, conventional analysis methods are further based on defining narrow selections around a presumed signal, while the rest of the dataset is discarded. The residual background is then modeled with a low-order polynomial. The first objective of this project is to define a non-parametric background model to enable end users to fit simulated signals directly to the full dataset. Another bottleneck of neutron scattering is that accurate simulations of the scattering process are often computationally expensive. While, for instance, detailed simulations of the instrument response function are available, they are usually not used due to the computational overhead. We aim to improve the situation by training a machine learning model on a small subset of the data. The fit can then be executed using the approximation that the resolution function is only slowly varying over the dataset instead of performing the simulation at every point. A third objective of the project is to ensure the optimal use of allocated beam time through an automated, intelligent decision-making system that will determine when sufficient data has been collected in an arbitrary measurement setting. Consequently, the experimental protocol should then advance to the next setting.